Not long ago, and thanks to the observations of distant supernovas obtained by the Hubble Space Telescope, astronomers were able to conclude that the universe was not only expanding but also accelerating. In the 1920s, Friedmann introduced the possible fates of the universe, which included a flat universe, a collapsing universe, and an expanding universe. It was not until 1929 that Edwin Hubble and his collaborator Milton Humansson determined that the right model for the universe was one in which it was expanding. They came up with this conclusion with observations of distant galaxies, which not only appear redder than those close to us, but also the reddening increased with distance. Dr. Hubble calculated the mathematical relationship between the galaxy distance and the speed at which it travels away from us. The equation seems quite simple, and it included a constant which now is known as the Hubble constant, and is very important to determine the age and history of the universe. However, coming to a consensus on its value is not as simple. It depends on the method used, and the difference has important implications. That is why this difference is usually referred as the Hubble tension. So let's take a look at what astronomers are doing to determine this constant. One method follows the same approach as that of Hubble. It uses independent distance indicators or standard candles like Cepheid variables for the stars in the local universe and supernova for the more distant universe to determine what is the Hubble constant that fits the distribution with distance. The latest observation results in a value of around 73 kilometers per second per megaparsec. The second method uses a model that fits the Big Bang afterglow, also known as cosmic microwave background radiation. The cosmic microwave background can be better understood as temperature variations that trace the fluctuation in the density of matter in the early universe. In these models, the value of the Hubble constant is one of the parameters that need to be fixed, so together with the composition of the universe explain the properties of the cosmos and matches the cosmological observations. The value in this case comes to around 67 kilometers per second per megaparsec. Both values fall within the range describing an accelerating universe. However, the expansion rate used in standard candles significantly exceeds the model's prediction, giving rise to this so-called Hubble tension. The term tension here arises from the uneasiness astronomers feel after coming up with different values, which might mean that there is a different physics they still need to understand. In the method using distant indicators, the uncertainties can be reduced by using powerful telescopes like the Hubble Space Telescope that can separate the stars from their neighbors in distant galaxies. Now, we also have the power of resolution of the James Webb Telescope that also can see stars that are farther away from us. The Nobel laureate Adam Rees and a team of astronomers use these observations to improve the precision of the Hubble constant in the local universe. In the first year of the LST operation, the team collected observations of the 320 Cepheids found previously by HST, along with 4 more supernova host galaxies. These observations were needed to refine previous measurements, which could be affected by the dusty environments in the host galaxies and make the stars look redder than they really are. Using the sharp infrared vision of JWST and its power to look through dust, it also becomes possible to separate the light of the Cepheids from neighboring stars with little blending and reducing the noise in the measurements introduced by the presence of dust. Rees states that the JWST measurements provide strongest evidence that the errors in the measurements of HST do not play a significant role in the present Hubble tension, leading astronomers to believe that they are still missing something in the understanding of the cosmos. This difference might indicate that astronomers need to invoke exotic dark energy, exotic dark matter, if there is more exotic that talk about dark energy or dark matter, but also unique particle fields or probably even a new understanding of gravity. For sure, the study of the origin of and history of the universe will continue to be the focus of intense research in the coming years.